We continue now with chapter 12, static equilibrium. If you take a look at the word static means, we kind of not going to be having any motion, and equilibrium refers to some balance which is in place. If you look at the two pictures I have on the cover slide, the first is the Leaning Tower of Pisa. This is in Italy. It's actually a tower that was built in the 12th century, and it's leaning at an angle of 4 degrees. It's leaning because the ground that they built it on was soft, but luckily the foundation, the walls at the base, are in the order of 2.5 meters thick, which is providing it with some stability. And what we're going to be looking at is under what conditions would a tower such as this or a Jenga tower remain stable, remain in static equilibrium, and not in fact fall over. So the learning outcomes for this chapter are that you should be able to state the conditions for static equilibrium and then apply these conditions to solve problems on static equilibrium. For a rock on the ground, of course, its acceleration is going to be 0. It's just standing still. This means that the sum of the forces is 0. If we have a moon in orbit around the Earth, its angular acceleration is 0. This means that its orbital trajectory isn't speeding up or slowing down. And this implies that the sum of the torques is 0. So for us to have static equilibrium, both of these conditions must be satisfied at the same time. That is to say, the net external force on the object must be 0, and the net external torque on an object about any axes must also be 0. Right, so this chapter really is about solving problems, and how we're going to go about it is I'm going to talk you through a few examples, highlighting the key points in the solution, and then I need you to really go home and practice the solving problems on your own. The formula we're going to follow for solving problems is we're going to start with having a sketch of the situation. We're going to have a force diagram showing all forces acting on the relevant objects, and then we're going to resolve the forces into their components according to a suitable axis. These 3 steps are something we've already done in previous chapters with our work on Newton's law. The next step we're going to do, number 4, is choose an appropriate axis of rotation and then apply the 2 conditions that we've seen before. That is that the net external force must be 0, so the sum of all the forces must be 0, and the second condition is that the sum of the individual torques must be 0, or the net external torque must be 0. So these final 2 steps, they relate very strongly to what we did in the previous chapter in terms of torque. Applying the 2 conditions for static equilibrium will allow us to write out a number of equations, simultaneous equations. You'll remember before, if you have 2 simultaneous equations with 2 unknowns, you're able to solve for those 2 unknowns. If you have 3 unknowns, you need 3 simultaneous equations to solve for those unknowns. So in general, if you have n unknowns, you will need to create n simultaneous equations to solve for those unknowns. Okay, so let's get down to work and look at an example. A seesaw consisting of a uniform board of mass m and length l supports at rest a father and a daughter with mass mf and md respectively, as shown in the figure. So we have a seesaw, and they say that there's some board with mass m, so this board has mass m. We have a father and a daughter, and we're given their masses as mf and md. The support, called a fulcrum, is under the center of gravity of the board. They're referring to this triangle structure here being the support or the fulcrum. It's under the center of gravity of the board. The father is at a distance d from the center, and the daughter is at a distance L/2 from the center. So we're given the distance from the center to the father is distance d, and the distance from the center to the daughter's position is L. And then we ask two things. The first thing is determine the magnitude of the upward force exerted by the support on the board. So this is going to be the normal force shown here. We'll need to calculate this vector n, and determine where the father should sit to balance the system at rest. So here you can see the father should be seated at some distance d. So for the second part of the question, we asked to calculate this distance d. As I said before, these are the steps that we're going to be following. So the first step is to start with a sketch and to indicate all the individual forces acting. So we're going to have the father, and the one force we're going to have acting is the force of gravity on the father, which is going to be mfg acting downwards. Similarly for the daughter, we're going to have a force acting downwards on the daughter. For this problem, our object of interest is this beam or wooden bar that they're sitting on. And we're given that this bar has a mass of cap m, and for us to represent the force of gravity on a bar, we concentrate the mass at the center of the mass of the bar, which will be in the middle of the bar, and then we indicate the force of gravity on the bar as cap m times g. The other force that we have is the normal force. It's the normal force of the fulcrum on the bar, and we represent this by n as shown here. So remember, the two quantities we're trying to solve for is n, and the second quantity is d, the position where the father should sit. If we go ahead and take a look at the steps that we're following to solve the solution, the next thing we need to do is resolve the forces into their components along a chosen axis, and then choose an appropriate axis of rotation. So let's take a look at those two steps. The best choice of axis would just be the standard XY axis without it tilted or rotated. So that's to say that we would use, this would represent the Y axis and the X axis would be represented as such. The next step we need to do is identify an axis of rotation. Well, think about what would happen if this seesaw wasn't in static equilibrium. Then this girl might be moving up and down with her father moving down and up, and this beam would be rotating around this point, right? So we choose this point here at the fulcrum as being the axis of rotation. The next thing we need to do is apply the two conditions of static equilibrium. So the two conditions are, firstly, that the sum of the external forces must be 0, and secondly, the sum of the external torques must be equal to 0. So taking a look at the first condition and applying it, we've identified all the forces. So we need to take their signs into consideration, and we see the individual forces are the normal force acting in the plus y hat direction, mfg, the mass of the father, times g, the force of gravity on the father. This is acting downwards, which is in the negative direction. There's also the mass of the daughter, resulting in the force of gravity on the daughter downwards, so it's minus mdg. And then we also have the force of gravity on the beam, right? And this is also acting in the negative direction. So we have minus cap mg, and the sum of these must be 0. So we've included our 1, 2, 3, 4 forces. The second condition that we need to satisfy is that the sum of the external torques must be equal to 0. And each of the father and the beam or the bar and the daughter, they're each going to have an external torque associated with them. So let's have a look at each of them individually and see what their torques are. Remember, this is the general expression that we had for torque. It's given as the cross product of a position vector r and a force acting, and we use the sign convention of positive for counterclockwise and negative for clockwise. If we look at the torque resulting from the father, well, the father would be moving downwards under gravity, which would cause this whole bar to rotate counterclockwise. And for this reason, the sign of the father's torque is going to be positive. For counterclockwise, we have positive. So the sign of the father's torque is going to be positive. Remember, we said the axis of rotation is situated here. So the position vector, it's from the axis of rotation to where the father is. This is distance d. So this is where this term comes from here. The third term is the force of gravity on the father. This is the force acting downwards, which is mfg. So this is the third term, and the angle between the position vector and the force is 90 degrees. Moving on to look at the second object, which is the beam or the bar. It's also going to have a torque associated with it, but in fact this is a trivial torque. You can notice this, that if you note that the center of the mass of the beam or bar is in the middle, and this is at exactly the same position as the fulcrum. So this means that the position vector from the center of mass of the beam to the rotation axis is going to be 0, right? So we have that 0 there. So we have 0 multiplied by mg. This term is going to be 0. So the beam or the bar isn't going to contribute to the total torque. The torque of the third object, we take a look at the daughter. For the daughter, we note that if gravity were to pull her downwards, then this would result in a clockwise rotation of the beam or bar. Have a look at that carefully for yourself. If the daughter is going to be pulled down by gravity, then this whole beam or bar is going to be moving clockwise. So for that reason, the sign associated with her torque is negative for clockwise rotation. The distance, her position vector from the axis of rotation to where she is, that's a distance of L over 2, right? And it's a distance of L over 2, that's this L over 2. And the force relating to her is the mass of the daughter times g. That's where that term comes from. The final thing we need to include is sine of the angle. Well, the angle between the position vector and the force is 90 degrees. This angle here is going to be 90 degrees. So for that reason, when calculating the torque of the daughter, the angle's sine of 90 degrees. If you look at each of these terms, remember sine of 90 degrees is going to be 1. So this is just going to be, the torque of the father is just going to be plus d mfg. The beam isn't going to contribute anything because of this 0 term, and the daughter is going to contribute negative L over 2 mdg. So this means that if we combine these three terms into this equation here, the sum of the torques is equal to 0, then what we get is the contribution of the father combined with the contribution of the daughter is equal to 0. Just to remind ourselves, the two things that we're trying to solve is we're trying to solve for d, the position where the father must sit, as well as the magnitude of the normal vector n. And now what we find is we're able to solve for n and d from our two equations. Equation A can simply be rearranged to make n the subject of the formula, and we can see that mf, md and cap m, they're all knowns. So this is the solution then to find the normal force. Secondly, from equation B, we're able to rewrite d in terms of this expression here. We've rewritten d in terms of the mass of the daughter, the mass of the father, and the length of the beam, which are all knowns. So this thing gives us the solution, which we found considering our two conditions for static equilibrium. The first is that the sum of the external forces is 0, and the second condition being that the sum of the external torques must be 0. We now take a look at another example. A uniform horizontal beam with a length of L equals 8 meters and a weight of WB equals 200 newtons is attached to a wall by a pin connection. So here we have a beam, and we told it has a length of 8 meters and it has a weight of WB equals 200 newtons. And it's attached to the wall at this point here by pin connection. Its far end is supported by a cable that makes an angle of phi equals to 53 degrees with the beam. So here we have a cable that's holding the beam up, and we're given this angle phi is 53 degrees. A person of weight WP for person equals 600 newtons stands at a distance of D equals to 2 meters from the wall. So here we have a person standing here, and we told his weight is 600 newtons, and he's standing at a distance of D equals to 2 meters from the wall. So the distance from the person to the wall is 2 meters. Find the tension in the cable, the tension in this cable, as well as the magnitude and the direction of the force exerted by the wall on the beam. So we asked to find the tension in the cable as well as the force exerted by the wall on the beam. Remember that the beam is going to be pressing into the wall, and the wall is going to be applying an equal but opposite force at this point here. Right, so we begin this problem. Immediately we can identify the object that's going to be rotating is going to be the beam. You can imagine what happens is if the string were to be cut, then this beam would drop down, right? It would fall down. It would rotate in a clockwise direction, and it would be rotating about this point. It would be pivoting about this point. So our object of interest is going to be the beam, and this is going to be the axis of rotation over here. And something else for us to just bear in mind in our initial reading of the problem is that when we have a beam, we're going to be representing it by a point of center of mass, which will be a point at the middle of the beam. So going on to solve the problem by firstly identifying all the forces acting, and then breaking the forces up into their x and y components. We note that, okay, so as I already discussed, the object of interest is the beam, and the mass of the beam is located at the center of mass of the beam, which will be in the middle. So if we look at all the individual forces acting, the first force is going to be the weight of this person, which is going to be acting downwards. Over here we've indicated this is WP, the subscript standing for person acting downwards. The second force applied to the beam is going to be the force of gravity on the beam, and we represent this as WB, a force acting at the center of mass of the beam, acting downwards. Then we're going to have a rope which is holding the beam upwards, and this is going to be there's going to be some tension in the rope which is pulling the beam upwards. So this is going to be our third force, as represented here by T, acting in the direction as shown, and an angle of phi. The fourth force is going to be the force of the wall on the beam, which comes about from Newton's third law, and this force we've represented by R, by vector cap R, capital R, and we're not sure at what angle this acts, so we've just put in some angle and called that theta. The orientation of our x and y axis would just be as per normal. So the next thing we need to do is break these different forces up into the x and y components. We can see this force R, it will have a y component, R sine theta. It will have an x component, R cos theta. For the weight of the person, WP, we see that this is already acting downwards. For the weight of the beam, this is represented by a force acting at its center of mass, which is going to be in the middle of the beam at a distance L/2. We don't need to break this into any further components because we can see that it's pointing in the minus y direction. Finally, the additional or the final force that we need to break into its components is the tension of the rope, and here the relevant angle is phi. So the y component is going to be t sine of phi, and the x component is going to be t cos of phi. So that represents then each of the forces broken into their x and y components. Now we come to applying our two conditions for static equilibrium. The first being that the sum of the forces is equal to 0. Well, we need to apply this in the x direction as well as in the y direction. When we apply it in the x direction, we can see we have r cos theta pointing in the positive x direction minus t cos phi pointing in the negative x direction is equal to 0. When we apply the sum of the forces in the y direction, we can see we have r sine theta pointing upwards in the positive direction plus r sine theta. The second y component is we have plus t sine of phi, and then we have the weight of the person acting downwards minus WP, and the weight of the beam acting downwards. The second equation represents the sum of the forces in the y direction. Coming then to the second condition, that the sum of the torques must be 0. We note that for each of the forces acting in the y direction, we're going to have a torque, where the torque is going to be given by an expression in this form. So taking a look at our sketch, then we notice that over here, that this is going to be the axis of rotation. The axis of rotation is going to be here. So the position vector for the first force, this r sine theta force, its position vector will be 0. So the torque given by this force will consequently be 0, and we don't need to worry about it. The second force of consideration is the weight of the person, WP. WP is going to cause the beam to rotate clockwise. So for this reason, the contribution of WP is going to be negative. So this is where this negative sign comes from. The force is going to be WP, and the distance, the position vector from the axis of rotation to where the force is acting, this is d. So this explains where this term comes from. Similarly, for the weight of the beam, this is a force acting in the middle. We see the position vector, the distance from the axis of rotation to where the force acts. This is going to be a distance of L/2, half the beam, L/2, multiplied by the weight of the beam acting downwards, multiplied by the angle between the two, the angle between the position vector and the weight acting downwards. This angle is going to be 90 degrees. So sine of 90 is just 1. So that's why that doesn't appear. The third force that's acting is this T sine phi. We see that it's going to cause a rotation in the counterclockwise direction, which corresponds to a positive sign. And the magnitude of the force is going to be T sine phi, and the position vector is going to be the length of the beam. That's the distance from the origin from the axis of rotation to where the force is acting, the length of the beam, L, which then is this quantity here. So for each of these three forces, then 1, 2, and 3, we have a torque term. And as I said when we started, that this fourth force over here isn't going to contribute a torque term because its position vector is 0. What we're interested to find in this problem is three unknowns. We're interested to know what t is, what r is, and what theta is. And actually what we've done thus far is we've created three equations. Equation 1, equation 2, and the third equation comes from this condition that the torque be 0. So the rest of the problem involves some mathematical footwork to actually use our math skills to solve for these three unknowns. You can see from the third equation, we can simply rearrange the third equation, and by doing so can make t the subject of the formula, and we're able to then calculate t to be 313 newtons. Now that t is known, we're able to use the first and the second equation to solve for the other two unknowns, which are r and theta. And having two equations with two unknowns, this can be done by making use of some mathematical manipulations. What we actually do is we divide the second equation by the first equation, and by doing so we're able to make use of the fact that sine of theta over cos of theta is equal to tan of theta, and this allows us then to go on to solve for theta and find that it's 71.1 degrees, and then to substitute back into the original equations and find that r is equal to 581 newtons. So what I'd like you to do is to work through these mathematical steps yourself and make sure that you follow and understand the individual steps. In terms of the physics involved in what's important for you to know for this course and to concentrate on, the most important part of the problem is that you be able to apply the two conditions for static equilibrium and come up with the relevant equations. The solving of the simultaneous equations, that's also important, but what's most important in terms of the test and exam, and where most of the marks in the question will be assigned, is for correctly applying the conditions to come up with the simultaneous equations. The final problem we're going to be solving, it involves a ladder resting against a wall, and it actually also involves friction. So a uniform ladder of length L rests against a smooth vertical wall. The mass of the ladder is m, and the coefficient of static friction between the ladder and the ground is mu s equals to 0.4. Find the minimum angle, theta min, at which the ladder does not slip. So we asked to find the smallest angle at which the ladder does not slip. Note that the force of friction is simply included as an additional force. So we go about solving the problem as before. We have our ladder, and we introduce the different forces acting. The first force is the force of friction. So remember, if the ladder slips, then this point will be moving towards the left. So this means that friction is going to be acting in the opposite direction towards the right. We have the force of gravity acting on the ladder, and again we treat this as at a point in the center of mass of the ladder. And then we also have the force applied by the wall on the ladder at this point in this direction, and the final force under consideration is the normal force, which is going to be acting at this point. We apply the first condition that the sum of the forces must be equal to 0. Applying it along the x direction, we see that the plus Fs, the force of friction, minus the force of the wall against the top of the ladder is equal to 0. Applying it in the y direction, we see plus the normal force minus mg is equal to 0. Next it comes to applying the condition that the external torque must be 0. So we note that the axis of rotation will be at this point over here, and for this reason we don't need to worry ourselves with the normal force or Fs in the torque calculation. The reason for this is that the position vector for these two forces will be 0. So the only forces which we need to consider is this force mg, the torque resulting from mg, and the torque resulting from this force P at the top. So looking first at the force resulting from this force P, the torque resulting from this force P, we note that the length of the ladder is L, and the size of the force is P. It will cause a counterclockwise rotation, so its sign will be positive, and the angle over here, theta, will be the same as this angle at the top. So using this angle at the top, then we given the torque is PL sine theta. Next comes us to look at the torque caused by this force mg. We note that this force is going to cause a clockwise rotation, so its sign is going to be negative. The size of the force is mg. It's acting at a distance L over 2. That's because it's acting in the middle of the ladder. So this is where this L over 2 comes from. Now the angle is going to be this angle between the position vector and the force. And we can see that this angle here is going to be it's going to be 90 minus theta. And so what we're going to have is we're going to have the force mg multiplied by the displacement vector, which is L over 2, multiplied by sine of 90 minus theta. And sine of 90 minus theta is actually cos of theta, which explains where this cos of theta term over here comes from. This thing gives us our three equations for this problem, and using these simultaneous equations we would be able to solve for the unknowns. I leave that to you as an exercise. Right, so this brings this chapter on static equilibrium to an end. As you can see, there's a heavy focus of this chapter is firstly to know the two conditions for static equilibrium and then use those two conditions to solve problems.